Hello everyone, my name is Nidhi Singh. I'm an assistant professor in Gyan Vihar School of Pharmacy, that is a part of Suresh Gyan Vihar University, Jaipur. So today we are going to discuss aliphatic amines in this company of sustainment, that is a pharmaceutical organic chemistry first. And today we are going to discuss this aliphatic amine. In our last lecture, we have already discussed that what are aliphatic amines, what are the nomenclature of this aliphatic amines, and the properties of this aliphatic amines. So let's start. The learning objective of this aliphatic amine is that today we are going to discuss about this amines and also here to study about the stereochemistry of amines, that what is the stereochemistry of amines, and to study about the separation of a mixture of primary, secondary, and tertiary amines. These are the learning objective of this topic, and the student outcome they will going to know about what are amines. They will also learn about the stereochemistry of amines, and they also learn about separation of a mixture of primary, secondary, and tertiary amines. Let's start the topic. So the stereochemistry of amines, that amines are classified into primary, secondary, and tertiary based on the number of hydrogen atoms that are replaced by the alkyl or the aryl groups. So this is the stereochemistry. Here we are going to discuss the stereochemistry of your alkene. Amines are classified, as we already discussed, that they are classified into primary, secondary, tertiary amines based on the number of hydrogen atoms that are replaced by the alkyl or the aryl groups. So here, from the ammonia, the your hydrogen atoms have been replaced by the alkyl or the aryl group. On that basis, they are classified into primary, secondary, and tertiary amines. And the tertiary amines have three different groups, that is the R1, R2, and the R3, that is attached to the nitrogen atom. They are asymmetric or chiral, and therefore they do not form superimposable mirror images. Tertiary amine exists in two enantiomeric form. This is due to the inability of unshared pair of electrons that are present in fourth sp3 orbital of nitrogen to serve as a fourth group to keep configuration. So in the stereochemistry of amine, in the stereochemistry of amines, the amines are classified on the basis of their hydrogen atom that have been replaced by the alkyl and the aryl group. So they are classified into primary, secondary, and tertiary. In case of primary, the one hydrogen is replaced by the one alkyl group. And in case of secondary, the two hydrogens have been replaced by the alkyl group. And in the case of tertiary, the three alkyl groups has been replaced by the alkyl group. So alkyl or the aryl group. So the tertiary amines have three different groups, that is your R1, R2, and R3. They are attached to the they are attached they are attached to the nitrogen atom. So in the tertiary amines there are three different groups, R1, R2, and R3. They are attached to the nitrogen atom because in that the three hydrogens have been replaced by the three different alkyl groups. So they are asymmetric or achiral. They are asymmetric, means all the three carbon alkyl groups that are attached to this tertiary nitrogen in this tertiary amines, they are all asymmetric and they form a asymmetric or chiral, and therefore they do not form superimposable mirror images. They are not forming any superimposable mirror images. So they are not superimposed on each other. So the tertiary amine exists in two enantiomeric forms. So this tertiary amines are existing in two enantiomeric form, and this is due to the inability of unshared pair of electron present in fourth sp3 orbital of nitrogen atom. And uh, uh, this uh, this this tertiary amine which is existing existing into an enantiomeric form. And why this is existing into an enantiomeric form? Because of the inability of the unshared pair of electrons present in fourth sp3 orbital of nitrogen to serve as a fourth group to keep configuration. So in this case, they are forming, they are having incapability of unshared pair of electrons present in the fourth sp3 orbital of nitrogen to serve as a fourth group to keep a configuration, and that is why they are existing in two-dimensional form, as well as they are forming a asymmetric and or sorry chiral, and therefore they do not form superimposed images. And they are existing in two-dimensional form, and this is due to the inability of unshared pair of electrons present in the fourth sp3 orbital of nitrogen to serve as a fourth group to keep configuration. So here, as you can see, this primary amine, secondary amine, and the tertiary amine in this. In the primary amine, the one alkyl group is attached. In the tertiary secondary group, there are two alkyl groups are attached, and in the tertiary amine, there are three different alkyl groups are attached. This next. So in contrast, cautionary ammonium salt. In contrast, cautionary ammonium salt, in which the nitrogen atom is attached to four different groups. So cautionary ammonium salts, in this the nitrogen is attached to four different groups. And in cautionary ammonium salt, the group may also be chiral and able to form enantiomerism as well as optical activity. Because all the because the nitrogen atom is attached to four different groups. These are attached to four different groups, and in partially ammonium salt, the groups may also be chiral and also show enantiomerism as well as optical activity. So in this partially ammonium salt, the group that are attached to this partially this nitrogen, they are all chiral and they show enantiomerase property as well as their optical activity property. So this is because the nitrogen in this salt is tetrahedral and all its sp3 orbitals are involved in the bond formation. So this in this partially ammonium salt, this is due to the present because the nitrogen in this salt is tetrahedral. Because the structure that in this partially ammonium salt, in which all the different four groups are attached to the nitrogen atoms, they are all forming a tetrahedral structure, and all its sp3 orbitals, all the sp3 orbitals are involved in the bond formation. So this in this cautionary ammonium salt, the group also be chiral, and they also show enantiomerism as well as optical activity. So in contrast, cautionary ammonium salt, in which the nitrogen atom is attached to four different groups in cautionary ammonium salts, the group may also be chiral and able to show enantiomerism as well as optical activity. And this is because the nitrogen in this salt is tetrahedral and all its sp3 orbitals are involved in the bond formation. So the amines displays different characteristic infrared absorption peak based on the degree of amine. So if we are displacing this amine in the infrared absorption, so in the IR, so they are showing different absorption peaks based on the degree of amines. Means based on the type of the amines. Means primary showing a different absorption peak, secondary showing the different absorption peak, and tertiary showing the different absorption peak. So in this, the amines displays different characteristic infrared absorption peak based on the degree of amine. So the primary amines, they are containing two nitrogen-hydrogen bond, which displays two peak around 3300 centimeter inverse. The shape of higher peak is similar to the molar peak, hence also known as molar peak. So this primary means they are showing they are containing two nitrogen hydrogen bonds. So they are showing two nitrogen hydrogen because they are only one hydrogen is replaced by the alkyl groups. That is why they are showing the two bond, that is just nitrogen hydrogen bond, and both of them, the both nitrogen hydrogen bonds are displayed with two peaks that is around the 3300 centimeter inverse. And the shape of the peaks, the shape of the IR peak, the shape of the IR peak is similar to the molar peak. The shape of this IR peak is similar to the molar peak, hence also known as molar peak. So these are known as molar peak. And the secondary amines contain only one nitrogen hydrogen bond in that in the secondary amine. The two hydrogens have been replaced by the two alkyl groups. That is why they have only one nitrogen hydrogen bond. So it displays a peak, single peak around 3300 centimeter inverse. So here, this secondary amines is um, showing the peak at absorption peak at your 3300 centimeter inverse. In the case of tertiary amines, they are containing no nitrogen hydrogen bond because in that case, all the three hydrogen have been replaced by the three different alkyl groups. That is why in this case there is no nitrogen hydrogen bond and they do not show up in infrared spectroscopy. So they are not showing in infrared spectroscopy. So in this So this is the stereochemistry of amines, and I repeat again that the amines are classified into primary, secondary, tertiary, based on the number of hydrogen atoms are replaced by the alkyl or the alpine aryl groups in this amines. They are classified or they are divided into the types based on the number of hydrogen atoms that have been replaced by the alkyl or the aryl group. And in case of tertiary amines have three different groups. Tertiary amines have three different groups. So these three different groups, that is your R1, R2, and the R3 that are attached to the nitrogen atom, that are attached to the nitrogen atom. They are asymmetric, there is metric or chiral, and they therefore do not form superimposable mirror images. So they tertiary amines are asymmetric or chiral and they do not form superimposable mirror images. And the tertiary amines, these tertiary amines, they are existing in two enantiomeric forms. They are existing in two enantiomeric forms. And this is due to the inability of unshared pair of electrons. This is due to the inability of unshared pair of electrons that are present in fourth sp3 orbital of the nitrogen to serve as a fourth group to keep configuration and the in the third in the tertiary amines they are showing because in this the third three different groups are attached to the nitrogen atom, that is why they are showing a asymmetric and the chiral property and therefore they are not superimposable on each other. So here the tertiary amines are showing this property due to the inability of unshared pair of electron that is present in sp3 orbital, that is present in fourth sp3 orbital of nitrogen. This is serving as a fourth group of serving as a fourth group to keep configuration. And these are existing, these tertiary amines are existing in two enantiomeric form. So this is your primary, secondary, and the tertiary, and all the three are showing the pair of electron orbit, all the nitrogen atoms. And all here shown that the alkyl groups are attached to this hydrogen atom. And in primary, there are two hydrogen atoms that are bonded to this nitrogen, and one alkyl group is bonded to this nitrogen. In case of secondary, two alkyl groups are bonded to this nitrogen, and one hydrogen is bonded to this nitrogen. And in case of tertiary, all the three groups that are attached to this nitrogen, they are all the different groups that are attached to the nitrogen atom. So separation of a sorry. So in contrast, quaternary ammonium salt in which the nitrogen atoms attached to four different groups. But in case of quaternary ammonium salt, there the nitrogen atom is attached to four different groups. So in this case, in quaternary ammonium salt, the group may be chiral and symmetric and able to show enantiomers as well as optical activity. So in quaternary ammonium salt, they are not having the electrons present on them because all the three as well as the electron they are attached to the group, so they are showing the chiral and they are able to form the they have the ability to form the enantiomers as well as they are showing the optical activity. So this is due to the presence due to the nitrogen. This is because the nitrogen in these stars is tetrahedral and all of its sp3 orbitals they are involved in the bond formation and the amines displays different characteristics. Infrared absorption field based on the degree of amines and primary amines contain nitrogen two nitrogen hydrogen bond which displays 42 absorption peak around 3300. So here the amines, if we are taking the sample of this amine and we are displacing it in the infrared, so they are infrared spectroscopy. So in this, there are different characteristics which are shown by the different amines that you find primary, secondary, and the tertiary amines, and they are showing the different infrared absorption peaks and which is based on the degree of amine. And this is your primary amine. This primary amine is containing two nitrogen hydrogen because in this one hydrogen has been replaced by your alkyl groups. That is why it is showing the two nitrogen hydrogen peak and which is around 3300 centimeter. And the shape of the peak is just like the molar peak, and hence this peak is known as your molar peak. And in case of secondary amines, it is containing one nitrogen hydrogen bond and which is displaying out single peak around 3300 centimeter inverse. So in this case, in the secondary amine, this is showing one hydrogen bond, and this is displacing a single peak. And third is your tertiary amine. So in case of your tertiary amine, they are containing no nitrogen hydrogen bond because all the three hydrogen have been replaced by the alkyl or the aride group. That is why they are not having any nitrogen hydrogen bonds and they are not showing and they do not show up in infrared spectroscopy. That is why the tertiary amine is not showing any peak, any single peak in this infrared absorption, infrared spectroscopy. So next is the separation of a mixture of primary, secondary, and tertiary amine. If we have to distinguish amines from, it means that we have a mixture of the primary, secondary, and the tertiary amines, and how we will separate this mixture. So there are two methods. There are two methods that are used to distinguish the primary, secondary, and tertiary amines. So the two different methods which are used to distinguish the primary, secondary, and tertiary amine. That is the Ginsberg's method and Hoffman's method. So in this, the two methods which are used to distinguish the primary, secondary, and tertiary amines. That is your Ginsberg method and the Hoffman method. The first is your Ginsberg method. In this, the Ginsberg reagent is benzene sulfonyl chloride, and the primary, secondary, and tertiary amines can be separated by Ginsberg reagent test. So in the Ginsberg method, the Ginsberg reagent is benzene sulfonyl chloride, and this is the reagent, Ginsberg reagent, which is your which is used to distinguish the primary, secondary, and tertiary amines. And this benzyl sulfonyl chloride is formed by C6H5 Pl. So this is the chemical formula of this Ginsberg reagent. And in this, the primary, secondary, and tertiary amines. The primary, secondary, and tertiary amines, these are can be separated by the Ginsberg reagent test. And the primary amines react with Ginsberg reagent to form a precipitate of N-alkyl benzene sulfonamide, which is soluble in strong alkaline by KOH So in this, how it is separating the primary, secondary, and the tertiary amines by this Hinsberg reagent test. In this, the primary amine this is reacting with the Hinsberg reagent. This this primary amine is reacting with the Hinsberg reagent, and it is forming a precipitate that is N-alkyl benzene sulfonamide, which is soluble in strong alkali like KOH. So this primary amine, it is reacting. Firstly, it is reacting with this Ginsberg reagent, and there is a formation of a molecule. It is a formation of this intermediate, and this intermediate is again reacted, or it is reacted, or it is uh, dissolved in a strong alkali solution, and there it is forming a salt, and that salt is soluble in this strong due to this dissolving of this intermediate in the strong alkali. So there is a solubility in that strong alkali. So here you can see the primary amine is this is your primary amine. This is a Hinsberg reagent. It is specified here. So there is a formation of this monoalkyl sulfonamide. So monoalkyl sulfonamide is formed here. So this is your primary amine. This is your C6H5SO2Cl. So there it is forming this RNH SO2 C6H5. This alkyl group is attached to this nitrogen. So here it is formed monoalkyl because one is your alkyl, monoalkyl sulfonamide. So it forms monoalkyl sulfonamide. From here the Cl is removed. So from this monoalkyl sulfonamide is again reacted with this potassium hydroxide, which is a strong alkali. And then there is a formation of a salt. There you can see that there is a formation of this RNK plus SO2 C6H5 because there is the presence of your this lone pair. So there is a formation of this salt, and that salt is soluble in the strong alkali. So here in the aliphatic, this is your aliphatic reaction. Next, if you are taking the this reaction, aliphatic reaction, then this is your CH3NH2, that is your methyl amine. When methyl amine is reacting with this SO2Cl, that is your Hinsberg reagent, phenyl upon phenyl this SO2Cl is attached. So there is a formation of this monoalkyl sulfonamide. After that, it is reacting with the strong alkali, that is the KOH, potassium hydroxide, and there is a formation of the potassium salt, which is soluble in this strong alkali. So here, primary amines are forming a soluble. These are soluble in this Hinsberg reagent. Next is your secondary amines. So secondary amines are reacting with this Hinsberg reagent. They are forming a precipitate of this N-dialkyl benzene sulfonamide, which is insoluble in alkali. So this secondary amine is reacting with this C6H5SO2Cl. Then there is a formation of this dialkyl sulfonamide. So in that case, there is a formation of monoalkyl sulfonamide because there is only one alkyl group is attached to this nitrogen. But in this case, there are two alkyl groups are attached to this nitrogen. So it's formed. Then there is a formation of this dialkyl sulfonamide. So the secondary amine is reacting with this Hinsberg reagent, and there is a formation of this dialkyl sulfonamide. When this is reacting with this potassium hydroxide, there is a formation of this insoluble. There is a formation of this compound which is insoluble in this alkali. So this dialkyl sulfonamide is insoluble in this KOH, that is a strong alkali. But in case of primary, they are soluble in this KOH. But in case of your secondary amines, these are not soluble in the KOH. So there, this is your dialkyl, so dimethylamine. So in this case, this is reacting with this benzene sulfonamyl chloride, that is your Hinsberg reagent. There is a formation of this dialkyl sulfonamide, and this dialkyl sulfonamide is reacting with this KOH. then there is the formation of a insoluble precipitates are formed in this secondary amines in case of secondary amine. So next is your tertiary amine. So in the case of tertiary amine, they do not react with this Hinsberg reagent because they are not having any hydrogen in them. So they are not forming any reaction. So there is no reaction in this in Hinsberg reaction. So like this, we are distinguishing between these three amines, three amines like this. We are distinguishing with these three amines, and uh, uh, here, if the sample is given in the lab, that you have to distinguish this in this sample that what is your primary amine, what is your secondary amine, and what is your tertiary amine. So from this Hinsberg reagent, we are going to separate it. Uh, Separates these all the three amines. Firstly, in case of this primary amine, this in this Hinsberg method, they are not they are forming a soluble salt when they are treated with this strong alkali. Then in the secondary amine, they are reacting when they are reacting with this Hinsberg reagent. They are forming a they are forming a dialkyl sulfonamide, which is insoluble, and in case of your tertiary amines, they are not reacting with the Hinsberg reagent, so they are forming no reaction. So in the Hoffman method, the mixture of three amines is treated with diethyl oxalate, and the primary amines form a solid oxamide, a secondary amine that gives a liquid oxamic acid, while tertiary amine does not react. So in this case, this is your diethyl oxalate, which is your this amines are reacting with this diethyl oxalate in the Hoffman method. So the mixture of three amines is treated with this diethyl oxalate, but in case of the primary amines, they are forming a solid diethyl oxamate, and in case of your secondary amines, they are forming a liquid or diethyl oxamic ester. So here we have taken the two molecules of this primary amine. So when we are taking the two molecules of this primary amine and reacting with this diethyl oxalate, then there is a formation of this diethyl oxamate. So here a solid diethyl oxamate is formed. But in case of the secondary amine, there is a formation of the liquid oxamic ester. So here liquid oxamic ester is formed, and while tertiary amine does not react. While your tertiary amines, they are not reacting. So in case of your tertiary amines, these are not forming any reaction. They are not giving any reaction because in that there is no presence of hydrogen atoms in them because they are attached to all the three alkyl groups. Now, the mixture containing primary, secondary, and the tertiary amine is subjected to fractional distillation when tertiary amine, which is highly volatile, distill over, and the remaining residue mixture containing solid oxamic and the liquid oxamic esters are separated by the simple filtration. Both solid oxamic and liquid oxamic esters are separated, treated with a strong alkali like UH to recover and purified by the distillation. So when a mixture of this primary, secondary, and the tertiary amine, when a mixture of this primary, secondary, and tertiary amines, these are subjected to the fractional distillation. If they are subjected to the fractional distillation, then the tertiary amine, which is highly volatile, they are distilled over. And the remaining residue means here that the secondary and the primary, the remaining residue, they are containing solid oxamate and liquid oxamate ester. So here, in case of primary, they are when they are reactive with this diethyl oxamate, they are forming a solid oxamate. And when the secondary amines are reacted with this this oxamate, so they are forming a liquid oxamic ester. So these both of them, solid and liquid, can be separated by the simple filtration, and both solid oxamate and liquid oxamic acids are separated as treated with this this strong alkali, that is the potassium hydroxide, You can see that there we can recover and purified. After that, we can recover and purified by the distillation. So here it is your dimethyl oxamate, which is the solid, and it is treated with this KOH, and there is a formation of this potassium oxalate plus your primary amine is separated out from this method. And here in this case, the liquid ester, the when it is dealing with this strong alkalis, potassium hydroxide, there is the formation of the potassium oxalate, secondary amine, and ethyl alcohol is separated out. So we can easily separate this secondary amine and the primary amine from this. And next is your structural features affecting basicity of amine. So amines like ammonia are weak bases, and the basicity of amine is due to the presence of unshared pair of electrons or nitrogen atom which can share with other atoms. So in this case, the amines are weak bases, and the basicity is due to the basicity of the amine is due to the presence of the lone pair of electrons on this nitrogen atom. So that can be shared with the other atoms. So the unshared pair of electron create an electron density around the nitrogen atom, and the greater the electron density, the more basic the amine. So the electron releasing group, that is your methyl, ethyl, and other alkyl groups, they are increasing the basicity of aromatic amines, whereas electron withdrawing groups, they are increasing the basicity of aromatic amines. Thus, the basicity of aliphatic amines are increasing with the increase in the alkyl substituent as given below. So this in this case, the tertiary amine is having a more basicity, and this in this case it is having the secondary is having the low, then the primary is having the low, and the ammonias are the weak bases. Next, however, in aqueous solution, the order of basicity changes. In aqueous solution, the primary means basic, then the secondary, and this tertiary, and then ammonia. So the difference in basicity order in the gas phase and aqueous solution are the result of solvation effects, and the amines in water solution are existing as ammonium ions. So in this case, primary amine when is reacting with this water, there is a formation of this primary ammonium salt, and the secondary amine when is reacted with this water molecule, there is a formation of the secondary ammonium salt. And in case of tertiary amine, and when it is reacting with this water molecule, then there is a formation of this tertiary ammonium salt. So in water, the ammonium salt of primary and secondary amines, they are undergoing solvation effect due to the hydrogen bonding they are forming with the water molecule. So to a much greater degree than ammonium salt of tertiary amines, these solvation effects increases the electron density on the amine, and nitrogen to a greater degree than the inductive effect of alkyl group. So amines, they are act as a nucleophile in most circumstances, and the unshared pair of electron on nitrogen form a new covalent bond with hydrogen and displaces hydroxide ion. So here you can see this is your primary amine. So the primary amine is reacting with this water molecule, and there is a formation of this methyl ammonium hydroxide. So this is displacing the hydroxide ion from the water molecule and taking up the proton from it. So there is a formation of this methyl ammonium hydroxide. Next, the equilibrium constant. So the equilibrium constant for this reaction is as follows. So in this, the K equivalent is your equilibrium constant, that is equals to the CH3NH3 plus OH negative and the CH3NH2 and the H2O. So the base ionization constant equals to Kb equals to Ke equivalent, that is the value of your Kb for ethylamine is 4.37 into 10 raised to the minus 4, and the pKa is your 3.36. So the amines are basic in nature. The basic strength is stronger than the Kpa and value, and the smaller the pKb value, stronger is the base. So in this case, if the amines are basic that are shown in the table. So in this table, you can see that this is the basic strength of your amine. And in this, the ammonia is having the 4.74, which is a weak base. So here, this its constant is your P 4.74, and the primary amines, in the case of primary amine, the methylamine is having the 3.36, ethylamine is having 3.34, and the N-propylamine is having 3.42. So in case of primary amines, these are the this pK value, pKb value of this methylamine, ethylamine, and the N-propylamine. So here, in case of your secondary amine, the dimethylamine, that is a CH3 whole and 2NH, that is having the pKb value 3.29, and the diethylamine, that is having the CH3 CH2NH, which is having 3.02, and the dipropylamine, which is having pKb equals to 3.1. And in case of the tertiary amine, that is your CH3 whole and is attached to 3 alkyl group, it is having the pKb value 4.3, and the triethylamine, that is having, first is a trimethylamine, second is a triethylamine, and in this case, the pKb value is a 3.26. So here, this is the basic strength of the amine. And now in case of aromatic amines, the aniline is having 9.38, that is having the 9.38 pKb value. And in case of the N-methyl aniline, it is having NHCH3 9.15. And in case of NN dimethyl aniline, it is having 8.95. And the diphenyl aniline is having, in which there are two phenyl groups are attached to this amine nitrogen. So there, this is a secondary amine, and this is having the pKb value is 13.15. So the heterocyclic aromatic amine, the pyrrole which is having the nitrogen, and this is attached in the ring only. This is having approximately 14, and pyridine is also having the structure in which the benzene one carbon is replaced by the nitrogen, that is having the approx 8.7. And in case of the piperidine, that is having NH equals to 2.7. So here in this case, this is your basic strength. So in the basic strength, that the structural features, these are the structural features we are affecting, that is affecting the basicity of amines. And in this amines, these are these weak bases. They are having the 10 raised to power minus 4 to 10 raised to power minus 6 kb, and the basicity of amines is due to the presence of the unshared pair. So in this case, there is the presence of unshared pair of electron on the nitrogen, and the nitrogen um, which is which can share electrons with unshared pair of electrons with the other atom. This can form a bond with them. So the unshared pair of electrons, these are creating an electron density on the nitrogen atom, and the greater the electron density, the more basic is the amine. So if the electron density is more, then the more is the amine. And the electron releasing group, that is your methyl, ethyl, and the other alkyl groups, if they are attached to the nitrogen atom, then they are increasing the basicity of this nitrogen. And if an electron withdrawing group, means if the electron withdrawing group, that is withdrawing the electron from this nitrogen, then in that case they are decreasing the basicity of the nitrogen atom. So in this case, they are decreasing the basicity of the aromatic amines. Third, the basicity of aliphatic amines. So that is why the basicity of aliphatic amine increases with the electron releasing groups attached to the nitrogen atom. So in this case, if the alkyl group, that is your alkyl group, that is your CH3, if they are more attached to the nitrogen, then their basicity is increasing. So the tertiary amine, in which the more alkyl groups are attached to the nitrogen atom, in that case their basicity is increasing. More, and they are more basic in nature. So here the basicity of aliphatic amine is increasing with increasing alkyl substitution as given below. So this is your CH3, NCH3, CH3, that is a tertiary amine. It is having a more basicity compared to the secondary amine. and this secondary amine is having the more basicity than your primary amine, and the ammonia is your big base because it is not having any alkyl group or any of the electron releasing group is attached to this electron withdrawing group is attached to this electron releasing group is attached to this ammonia in the nitrogen. That is why it is a weak base, and it is having the less specificity as compared to all the three amines, that is the primary, secondary, and the tertiary amine. Next, in the case of this aqueous solution, but in case of your aqueous solution, the solubility is increasing because they are forming a hydrogen bonding. So the hydrogen bonding are formed more in this primary amine, that is your CH3 NH2, then your CH3 CH NH CH3, that is your secondary amine, and then this is your tertiary amine, and then ammonia. So the difference in the basicity in ordering the gas phase and aqueous phase are result of the solvation effect, and due to the solvation effect, there is a difference in the basicity of this there's a difference in the basicity order in the gas phase and the aqueous solutions, and this is resulting due to the solvation effect, and the amines in water solutions, amines that are in water solutions exist as ammonium ions. So these are showing these amines are solutions are existing as ammonium ions in this the primary amine when they are dissolving with the water molecule or where they are reacting with the water molecule. They are forming a primary ammonium salt. So they are forming a primary ammonium salt with them. And the secondary amines, in the case of the secondary amine, they are forming the water molecule. When they are reacting with the water molecule, then they are forming a secondary ammonium salt. And the tertiary amines, when they are reacting with this water molecule, they are forming the tertiary ammonium salt. So in water, in case of the water, the ammonium salt, this ammonium salt of primary and secondary amines, these are undergoing solvation effects. That is, the solvation effect is due to the hydrogen bonding. So it is due to the hydrogen bonding, and in this to a much greater degree than ammonium salt of tertiary amines. And these solvation effect, this solvation effect, which is due to the hydrogen bonding, this is increasing in the electron density. This is increasing the electron density on the amine and nitrogen. These are increasing the amine nitrogen to a greater degree than the inductive effect of the alkyl group. So these are due to this solvation effect, they are increasing the electron density on the amines, and they are increasing the electron density on the amines and nitrogen to a greater degree than the inductive effect of the alkyl group. And amines, thus they are acting as a nucleophile because they are having a nuclear presence on the nitrogen atom. That is why they are acting as a nucleophile. So nucleophile means a nucleophile has a property to donate electrons. So that is why they are donating electron in case of H2O. So here, in this case, this in methylamines, they are reacting with this water molecule and they are forming a methyl ammonium hydroxide. So there is a formation of this methyl ammonium hydroxide, and from here, they are forming a covalent bond with the hydrogen atom, but they are not forming, but they are displacing the hydroxide ion from this water molecule, and they are forming a bond. They have formed a bond with this hydrogen atom, because in this case, the amines are acting as a nucleophile and the hydrogen is acting as a electrophile. So this is the equilibrium constant of this reaction, and this is in this the amines are basic in nature. The basic strength is due to their pKb value, and this is the pKb value of the different amines that are shown in this. There is a basic strength of amine in the case of aromatic amine and in case of heterocyclic aromatic amine. So all the aliphatic amines, they are having the same base strength, and their pKb lies between 3 to 4 and are slightly stronger bases than the ammonia. So the increase in basicity compared with ammonia can be attributed to a greater stability of an alkyl ammonium ion. As for example, this is our CH2NH3 positive is compared with the ammonium ion, that is your NH4. The greater stability arises from the electron releasing effect of alkyl group and the resulting partial delocalization of the positive charge from nitrogen onto carbon in the alkyl ammonium molecule. So here the quotient nitrogen atom of the ammonium group is hybridized, that is the sp3. The how many structural elements are possible in this, that is 4. C3 acid and cannot represent by the quaternary ammonium salt. Then the IUPAC name, the first one is correct. Like what is used in preventing this causes, that is your lactic acid, and what is mixed in the release like mosquito attractant, that is your lactic acid. Amines which are bonded in alkyl groups are primary amines, and the trimethylamines is an example of your tertiary amines. And these are the references for this topic. Thank you so much for today's lecture.